Brad, did you want to make an announcement?
Yes, for homework, as you remember from your homework assignment, it says you have to pair with one of your classmates, right? So you're able to submit one homework, but you have to submit separately, individually, because each of you have a column in Blackboard to have a grade. So therefore, you have one homework, but both of you have to submit on Blackboard. And just type your name, both students' name, and ABC 1 to 3, that's it. And it's not a group assignment, it's individual. You have to go to assignments folder and submit your homework.
And let me give you what's happening in the next few weeks. I've instructed Ikram to start working on experiment number 1 next week. With the help of Berat, you will have a sign-up sheet on Blackboard. You can sign up 2 hours at a time to go on the reserve the station for your experiment. And similar to what he just said, when you finish with the report of experiment, each individually duplicate the uploading. Homework number 2 will be a combination of forward inverse kinematics, trajectory planning, one that Patrick is going to give you on Python and ROS. And next week, I think Berat is going to open the door for you on robotic toolbox and fuzzy logic toolbox that you could use for controlling robots in future homework. And this, what Patrick is telling you, he has 3, 4, 5 years of experiment with ROS. It's a very steep learning curve. So almost every student that I have assigned for you to work with your projects, almost each of them, they know ROS. So it's a work in progress, learning Python and ROS. I hope that by the end of semester, you feel much more comfortable with both Python and ROS. Okay? Therefore, don't get discouraged that it's too difficult right now, but that guy has got 2 years of work on that. Even he said it was difficult to learn it. Okay? So, don't get discouraged. But work with your partner. Like, for example, Ikram is working with the snake robot. He knows Python, and Nico, right here, sitting here next to Nicholas, he knows Python, he knows ROS, and he's also leading one of the teams. So you could pick the brain of your leaders and learn Python. Okay? And end of semester, I expect each of you to revise your resumes. Okay? To get more enhanced job future for you. Those are you going to work.
Okay, I got my better editor working. So we're going to look a little bit at my more complicated example. This one's actually in C++. So most people that are Python friendly, they're not going to really like this. But this is to show you again why you should probably use Python for starters at least. There are some things, of course, that you will need to use C++ for. There's no fast approach in Python for point clouds or the depth data, which I can show you. So, being that as it is, here is part of code to basically state all our different variables that we wanted to publish. At the time of creating this code, we didn't really consolidate a lot of our messages into one, because you can actually have a single message type that includes all those wonderful publishers that you see on the screen. So instead of just a whole bunch of boxes coming out of the program, you go into some other box that's probably just taking all of them back in, like a huge bus. You can actually just make one larger message that has everything, which is a lot like the twist message, which I might as well show you. We were talking about it last time. So ROS topic echo is the command you want to use to do this. Just dump everything to the command line. That's what ROS topic echo does for a particular topic. So in this case, this is the I'm you on board the Kabuki robot. So what you can tell by returning is that these numbers actually change a little bit. Which numbers you cannot really tell, right? So I think it's ROS message info. Sorry, ROS message show. Even the ones that know the most still have to look up the help sometimes, so don't worry. So this twist message, which is of the geometry messages twist, and geometry messages package. Like I showed last time, twist is composed of a linear and angular velocity. But we want to look only at something that makes sense for us. So we may want to look at the angular. So you can append the name of the the message within the topic. You can get just a little bit less out of it. Sometimes they're named a little bit differently. Oh, we actually just want to look at orientation on this one. So here's the orientation. Can you tell me what that is and won't pitch you up? Oh, you can't. This doesn't look like roll pitch out to me, right? Roll pitch out is three angles. This is not roll pitch out. This is quaternion. Quaternion is the three-space complex numbers, I, J, and K. So quaternion uses those numbers to create these X, Y, Z, and V, X, Y, Z, and W values that you can use to basically describe rotations. So this actually has some better than Euler angle properties. You see as it turns, it doesn't do something weird like in Euler angles where you go to 359 and you jump off the cliff and go back to 0, right? This goes from 0 to 1. So there's no discontinuity. So you can actually use that to control the robot. So the point of that was to show you that I could actually combine all these different publishers down into one message. This was the naive ROS programming that we had done in the beginning. And again, this has very limited use of functions, so bear with it. So this is just one example of what you could end up doing with ROS. As you saw before, when we were detecting young gun as red, and then the rest of the people wearing some little bit of blue, the target equals 1 is red. And I just put these in here for reference. 2 is yellow, 3 is blue. So just a reference, a little comment that you just leave in there. And then going down into it, C++ is ugly. And you try to look at it, debug it, whatever it is you want to do with it. So you set up a whole bunch of variables to their default values. And then you finally copy in the image. This is practically the same as a Python, just maybe a little bit more complicated looking. And then you get down into it, it gets a lot uglier in terms of indexing the image itself. Because on this one, I actually get down into the pointer, the image pointer, and look at very particular points of the image with reference to that pointer. In essence, I'm going through the image at each pixel, looking at the RGB values. That's all this thing's doing as a program. So right here, this is just, all this code on the screen is actually just to get that RGB value. I think Python, it's a one-line. Like a little one-line, minus the looping. So this is just this is actually just to initialize a matrix full of zeros. There are quicker ways, but this is just the one I want to use. So this is actually going into each one of the pixels, because it's actually, as I noted, there's different ways to store image data. This one happens to be, I believe, BGR, meaning blue pixel first, green pixel next, red pixel after that. If you try to do some sort of image processing in OpenCV, and you get some really weird static TV looking image, that's most likely what's happening is that you're looking at the data row. So this is like pixel 0, pixel 1, 2, 3, and so on. And just one long array that is like 3 times as long because it orders a BGR. That's where you see right here, the blue value, the green value, and the red value, with the offsets that are provided. So then, this is an openly available algorithm to find the red intensity with reference to total intensity of the pixel. And you do the same for the green, and then you can extract particular ranges, which I'm just telling you what this code is. You probably may not even understand what you're seeing here. But you look at particular ranges, and then you can say this red, green, blue pixel looks red. But you look at it in both the R and the G. And this is also the danger of using tabs.
Mm-hmm.
So if you're a Python programmer and you like to use tabs sometimes, you like to use spaces the other time.
All the time.
You like to mix it up, right? You are going to get angry one day at your program, and you're gonna try to ask somebody, why does my program look like this? That's because there's a lot of tabs in it. These tabs in different editors look different. In Nano, it probably look different than this. In gedit, it shows you the fact that one tab is about, 5, 6, 7 spaces. Somebody else might think that from one line to the next it should be 4 spaces. Everyone has a different preference. That different preference is bad. No one should have a choice. It should just be a bunch of spaces to the point where you're at. Be it 4 spaces per line, 3 spaces, whatever. You have to make a decision. Do it soon before you ask somebody to look at your code. So then all this part does is actually invert that pixel, change it from red to blue. And it turned out every pixel that I chose just kind of made it a blue color. Be it if it was the red, the yellow, or the blue. Inverting all the colors just kind of came out blue in there. So here's the target selection. You just put, if your target's 2, do all this stuff. This should actually be at the very start, so it doesn't go through all these other checks. But again, this is just naive ROS programming. hurry this up because we also build robots at the same time, sort of programming. So at the end, once you've done all your calculations, you know what you wanted out of whatever data you got in. Here's where you could draw stuff on your picture. In this case, it was all that GUI stuff at the bottom. Target located at pixel, whatever. It's at such angle from the center of the camera, so we can turn that way. And that's all just the drawing part. Really, it's just like 2 pages of drawing. And then at this point, in C++ at least, you can selectively publish your data. So I came across this get number of subscribers function for your publishers. So if you actually have somebody looking at the data, publish it. If they're not looking at the data, don't publish it. It seems like a very smart thing to do. Because honestly, you're putting all this data into your computer all at once. At every time you actually get a frame in processing. So you saw those frames were actually going pretty quick when we had the image real small. So every single time all that data is going, or not. So we were only looking at some parts of it. We were only looking at, say, like the image. We didn't need all this extra data. So we didn't actually publish it. And then just general C++ stuff. But this is kind of why you should probably stick with Python, at least for learning ROS. It's a lot quicker, a lot easier, a lot less places to make little mistakes. Look at all these different ROS topics. So all the ROS topics are the pink or purplish color. So we have the target position in X and Y, our corrected true target position, which is another crosshair, in X and Y, a theta, another angle, I forget why we used it, but we used it, and then a target distance, target total pixels, target true total pixels. So whenever you're working on something on a robot, you have to actually probably make a whole lot of calculations to determine whatever it is that you're doing. So if you're looking at like the centroid of like some colored ball that you're trying to track, you have to locate it in the image, but you have to locate it with respect to the camera lens, right? So just because it's over here, you just tell the robot to turn, or you tell the turn how much, or what speed. So you have to pay attention to those kind of things. So you may have to model it, and you may have to take some physics into account for how things are actually working, or else you're not going to get too far. And that's it for this file. I have another one, which is actually fun. I know you guys are loving this, me reading code. Here's another Python file. I have not described this one to you. It has a very basic controller. I actually made this for the undergraduate controls course. So what can we tell that this program actually does? What does it control? Can I tell you it's a control? Thank you. So the topic name is mobile-based man's velocity. And I told you last class that it's a twist message, which is basically how it moves in the linear and angular ways. So we're going to be publishing out of this controller. And this is just a very quick, sloppy Python program. Here are all our declarations at the beginning. So, going down to the bottom, here's what you could call a main in Python. So if the name of the program is main, then you would initialize this program with the name Kabuki controller in the ROS network that's on your computer. So your computer has a network of nodes. It manages all that for you. You don't have to say, this node is going to communicate with this other node at port 4,000, like 40,000 something. You don't have to do all that. You have to say that, you have to make all these different connections. You have to say which ports you're using. It really saves you guys a lot of time. I've done both ways. I prefer ROS. I will not show you the other way. I definitely won't show you it in Windows. But you could connect it technically with Windows if you wanted to. I just don't suggest it. So, what do you guys think this controller is going to do based on what I'm taking in? So it subscribes to two different things. A yaw set point, and also the IMU data from the robot. So what are we trying to do?
Set a direction.
Yeah. I should also tell you that this robot has I think it's like a single axis gyro. You can only get your heading from it. Meaning that it can tell how much it's moving when it moves, and only the angular z. So only about the z-axis can it tell what direction it's at. It doesn't have a full IMU, which would tell you what angle, inclination, everything you're at. It has different sensors for that, like the angle of the wheels. So this is a heading controller. And I'm hoping it just works right out of the box. Which package was it? Okay, so with gedit, you can barely see it, but on the top right here, when I hover over, you can't see it, but on the very top of the screen, you can tell what package you're in. This one happens to be Kabuki controller, you can barely read it in this time. So, ROS run Kabuki controller, controller.py. So how many people have actually seen a controller being used in real life? Very few, right? So this robot, if I turn him this way, he gets very angry. Because games are basically making him drive the maximum speed. You're not supposed to drop a robot like that, but these are actually kind of slow. So he goes back to his main heading, which he was at before. And you can see with all this data that's printing out, which you can get rid of, make your controller go faster, whole system work better, and if you're not printing all this stuff. Here's the angle difference that it sees from its original heading. So as I turn it, right now its original heading is basically where it was at the beginning. I can change the set point using the ROS topic. But as I turn it, it goes back to the position it was at. And that's only because it has properly configured games. So I have a few notes in here. That one is really slow. So if I use it at a value of 1, it's not very slow. It just takes a while to get back to it. And since I picked it up and turned it, it may not have known correctly that it had actually been changed, because before it was heading like this. But as long as it's on the ground, it has a better knowledge of whether or not it's been turned correctly. So there's some issues with sensors that you guys will learn. If you move it too quick for the sensors to catch it, it won't know. If you move it in a way that the sensors won't catch it, it won't know. So as you see here, it goes back to normal. So there's a little comment in here. 20 is really bad, don't do this.
Like B, you unplug the HDMI?
Yeah, because it's on my computer.
I was making sure.
Oh, it's only the network cable.
Oh, yeah.
Because my Wi-Fi wasn't working correctly, so the network cable was the last option, which worked after a while, apparently. Okay, so that's a bad controller. So it was trying to get to its set point, but it was never going to get there because the games were too hard.
Do it again.
Do it again?
Yeah.
I'm not sure how you would approve of this, but let's run it with the back controller again. So this is a very, very poor controller. It overshoots every time, and it tries too much. So once you close up the program, it stops. You choose a better controller. That's kind of what you have to learn on your own, and with the help of your advisors in your group. But if you've only really studied controls just in the classroom and never actually done anything with it, then you won't really know what's going on with it. So here's the beta controller once again. It looks nice. It controls what we need it to. The angular controller is actually very useful for your heading. So you're a robot trying to escape the room, you'd probably want a heading going that way, and then you turn, and then fall a little bit, and then turn again. When you're driving straight, sometimes you do have a heading change, which is only because you have two wheels that are exactly going the same speed because maybe you use one wheel more than the other one. Maybe, like in the case of the Roomba, there's actually air or something clogged in the wheels. So one motor is not working at full efficiency while the other one's working a little bit less good, I should say. So it's a very, very short program. It's more or less just print statements and comments telling you what not to do. So I will definitely share this with you guys because this was a fun one to learn myself. So Python has a lot of one-liner code that you can use. This is a very special case. It's kind of like declaring a function in one line. The lambda itself, the way it works is, let me just tell you what the O does first. So the O is basically the operator on the data that you put into the function. So O.x, O.y, O.z, O.w are the pieces of the IMU data that we saw on the command line that were being dumped out from the orientation, IMU data orientation. So that's those components. So the lambda operator, what it does is whenever you use this XYZ array, which I'll just show with highlighting, it works as a function on the orientation data coming in to this function. So as you see here, it's applied to it. And then you can finally use the ROS code, which will give you the Euler representation of your quaternion orientation representation. There's a lot of Asians in that sentence. But from that, you can actually get your Euler angles, and you can get something that you would identify with. But there are more advanced methods you can use to actually make a controller with this quaternion orientation. And as I stated before, full circle, NumPy is inside of ROS and necessary for ROS. Because you use NumPy to condition this array to get it into the right format. So basically, for the cloud guys, for the ROS guys, you're going to need to use functions like this sometimes. So, yeah, ROS is kind of like the thing that would actually push you towards the right direction, maybe in deploying many programs in, say, like the cloud or whatever. It's another way to learn. So, which actually you can actually deploy a lot of these ROS programs on the cloud. Which for the SLAM people, I'll show you guys how that works, because you're definitely gonna need it. But for that, I think that we are pretty much done. I've shown you all the examples that I have on this robot, as far as the image data, the heading. Of course, you can make it drive forward. I just didn't do it because I'm working on the table. Before, when I taught with this guy, I had it on a smaller table. I think I actually had it on like a little desk. So it's actually a pretty good experiment just having the rotation. You should actually do rotation before you do translation. To know that you're, like when you're doing control, that your translation controller is not the one at fault for the the bad action. Just eliminate a variable, then move on. And actually solve what your problem is. If you try to do both at the same time, you're really probably wasting a lot of time. So, any questions? Requests for code? Or I think that we're basically, I guess, done with the video. I can answer the question.